So, what were you supposed to do last night? And look. So, I didn't record that part where we were putting the numbers in there, but I'll record this part. If we make to the right positive, and we take that box and move it to the right, and time equals 0 is when we let it go, because that's what's expressed here. Time equals 0, it's at the 5 centimeter mark, we are letting it go. What is the velocity immediately when we let it go? It's on your little sheet thing. At t equals 0, what's v equal? 0. It's not moving. The instant you let it go, the velocity is 0. Of course, in addition to that, if the box is being pulled to here and you're letting it go, what direction will it travel immediately after it starts to move? I think to the left, which is the negative direction. I would expect that you started your graph in the negative direction. Of course, what do I put here and here? 0.4. This whole thing is bounded. So positive and negative. And what's this point? 0.385. And what's this point? 0.77 seconds. Now, that, of course, signals the end of class, but I would hope that you guys now have enough skills to understand that this should have been negative 3.3 meters per second squared. This is 0.385 seconds, and this is also 0.77 seconds. So in order to start this discussion, I want to kind of put everything up there that you should already know, but in maybe a slightly a different form. For example, we have expressions for period. Right? Something like t equals 2 pi times the square root of something, right? And we have frequency, which is 1 over the period, or by extension, 1 over 2 pi times the square root of something, right? Then I told you that there's a set of motion equations that go with this, and that I wouldn't take any time to tell you where they came from, just that they are the solution of a complicated calculus problem. But it came down to x as a function of time is x max times the cosine of something under the radical times t. Does that look familiar? And then velocity as a function of time was negative. What I put here was yesterday was like v max. Do you remember that? And put sine something under the radical times time. But if you look at your notes from the day before and just our notes from yesterday, we know that v max is x max times something under the radical. We proved it yesterday by looking at conservation of energy. And then a as a function of time was negative x max times whatever was under that radical squared times the cosine of the radical times time. All right? I'm leaving them all empty because if you've paid attention, you know that what's under the radical changes depending on whether we're talking about a spring mass oscillator or a pendulum. And there are different things for each. I want to explore that something based on these. And I want to make sure the way these are usually written is generic. That's how these are usually written. These are generic. All oscillatory systems look the same. They have the same properties, the same arrangement. Even this part, be careful here, because you know there's a difference between frequency and period. We divide the angular frequency by omega, and period is the inverse of frequency. So this is 2 pi divided by omega. These represent the base information for all oscillators. There's more things. There's energy and stuff, but energy is based on something else. 1/fkx squared is about springs. MGH is about gravitational potential energy. Yes, Miga? Coming back here for a pendulum, omega is G over L. For a spring mass, omega is K over M. And can you kind of imagine that there is any number of other types of oscillators that they too would have these things, present? And if it's not clear to you, let me keep making it clear. This has to be A max. It's in front of and defining the acceleration. So all of that must be the maximum acceleration, because cosine goes between max in one direction and max in the other direction. So that must be the maximum, right? When cosine is 1, that's going to be the biggest value the acceleration can be. Similarly, this has to be V max. For the same reason. Sine can only go between 1 and -1. This must represent the biggest value the velocity can be. Where does sine start? 0. So your graph should have started from 0. And sure you did, because there's a negative sign right here. Sine will have to be in the opposite direction of x max. So if x started to the right, the sine function tells you the velocity is to the left. Just a minute. And what I want you to do is pretty... Again, I want you to put the units in for K and M, and then simplify it all the way down to something that's just kilograms, meters, and seconds. A little better than the first period. That's good. So newtons per meter divided by kilograms. Good job. Good job. Which, of course, means kilograms, meters per second squared divided by kilograms. Divided by meters divided by kilograms. It's a whole lot of dividing in there. And let's try and make that a little bit smaller so that whole thing is on the top and the whole thing is divided by kilograms. It doesn't really matter. Kilograms and kilograms cancel. Meters and meters cancel. And we get the square root of 1 over seconds squared, which is 1 over seconds. And we talked about the fact that this can't be hertz. That this has to be something else. That the top is what? It's not very confident, even though I heard the word a couple, 3 times, but the top has to be that we understand this, because I've noticed that your understanding of this seems to be lacking. And I've actually talked to a math teacher, and I think I know why. So let's have just a brief reminder about something about math you're supposed to really understand, but I'm not sure that you do. Cosine returns a number with no units. And the number it returns has to be between 1 and -1, right? That's all it can do. That's why there's an x max out front. Your cosine tells you what percentage of the maximum displacement your object is at any one time. And since it can only go between 1 and -1, the biggest number that x can be is is x max, and the smallest number it can be is -x max. But small is probably the wrong word to use here, because we know that this represents a location. So the farthest to the right it can be is x max, and the farthest to the left it can be is x max. That's what this is telling you. But everything in here has to be an angle measure. you're taking the cosine, and the cosine expects an angle measure. And although there are several ways to measure angles, the way we measure angles is either radians or degrees. Something like this, which is being produced by other numbers, has to be in radians, which is why we say radians is a unitless quantity. It only shows the fact that it's an angle measure in the way in which it's used. So this thing under the radical is in radians, and it has to be, because in here, I'm taking that radians per second, and I'm multiplying by time, which is in seconds. So that what's inside the parentheses is an angle measure. Does everybody understand that? That's why it has to work this way. I know you're trying to write it down. Be fast. So, does it work? Check. Does it work? Right, this is the pendulum one, right? Does it work? G is in what unit? That's sad. What is the unit for G, please? Meters per second squared. What's the unit for L? Meters. That's right. This one's easy. G is acceleration of gravity, meters per second squared. L is meters. It's a length. It has to work out. It has to work this way. Now, here's where I'm going to ask a question, and I don't know that you guys have the answer. But I taught this to you 2 months ago. If I want to go from if I want to go from radians to rotations, what do I have to do? If I have a value in radians and I want to go to rotations, do I divide by 2 pi or multiply by 2 pi? This hurts my heart so bad. There are, if I recall, one rotation has 2 pi radians. So I think if I want to convert this, looks like I'm dividing. All right? Boy, that hurt. You see how that hurt my heart a little bit, right? I think the heart's on this side. It's hard to know. Mine's so small. But looks like if I have something in radians and I want rotations, I have to divide by 2 pi. Does it not surprise you then that we are dividing by 2 pi here? Do you understand why we're doing that? An oscillation is a rotation. In fact, a rotation is a type of oscillation. Going around in a circle brings you back to where you start. An oscillation is a more general term. So when we talk about this, it works the same way. I said when we first defined this that this was the oscillatory frequency. That's what I called it. This is in radians per second. It is the angular frequency. One's about oscillations, one's in angles. We divide the angular frequency by 2 pi to get the oscillatory frequency. That's why this will be in hertz, with our oscillations per second. But we have something else that's in radians per second already. When we did rotational motion, angular speed was radians per second. So angular frequency is often given the symbol omega. You ready for this? Is this enough? Oh, how about this? Are we good? All right. I didn't know how much I'd have to show you to have it dawn on you yourself. We okay now?